your homework for the chi-square is to do these two types of tests using our class data and data from the previous class that I'll give you. And the first one is you're going to examine the question, are students in biostats this semester more likely to be males or females? And in the second one, you look at, are students in biostats this semester more likely to be male or female than students last semester? In other words, does the probability of being male or female depend on whether or not students are in biostats fall versus spring semester, right? So two questions, two different calculations. We're going to do a lab on Thursday. We're going to go through these calculations in R, so you'll see how to do it. And also, I've got this chi-square 2x2 test calculation example that I'll walk through with you today. But all you have to do here is you write out the hypotheses for test one. And again, look at my example, look at the lecture, look in the book. The book has it all in there. And then you're going to put our observed frequencies of male and female and total, calculate our expected, assuming a even distribution, right? So how many students do we have in the class total? 23? Oh, 22. Oh no, wait, I think 21, because I think on our data sheet, it included Michelle and I. So you should be roughly 10 expected in each, something like that, if we had 20 students. How many do we have? 21, so 10.5. Yeah, the expected doesn't have to be a whole number. Expected can be a different value. So you just do the math. Observed minus expected squared, divide by expected. Just follow the procedures, do the math, sum it up. That's your chi-square. And then you'll just copy and paste this into R, run it, substitute your count one of observed male and observed female. Observed male is count one, observed female count two, or you can reverse them. It won't matter. Run this code and you'll get your result. You put in your p-value, whether or not you reject the null hypothesis, and your conclusions written as you do for saying, we think this is happening, chi-squared, degrees of freedom, p-value, right? This is easy. No problem. You'll get this just fine. For test two, it's a little bit more involved. It's a little more involved. Again, you write out the hypotheses, and here you have the observed for spring semester, last semester, and you will put in the same numbers of observed female and male for fall semester in your total, and you'll add up all your totals here. And then you have to calculate the expected, right? And this worksheet walks you through step by step exactly how to do that. Column one total divided by total. See, column one total is females divided by total over here. Column one total divided by total, it goes here. And that's the observed proportion of females in the class. And then you calculate the observed proportion of males in the class. Column two total divided by total. So your column two total is a total number of males in both classes divided by the total number of students from both classes. And that'll give you your observed proportions of males in the class. And then you say your observed proportion of females times the numbers in biostats, right? Row one total, observed proportion of females, what you calculated up here, times a number in biostats total is your row one total expected counts for cell A. All right, it walks you through, and then you just put in here your observed, your expected, square it, divided by expected. Observed, expected, squared, divided by expected. This is just a little table that basically does the same thing as this bigger table up here. All right. And then you run the test in R to do a p-value. Again, you'll just copy and paste this code into an R script, substitute your counts for the females in the spring, your males in the spring, females in the fall, and males in the fall. Run all this code and you will get a p-value and you can write your conclusions. And here I've included notes on interpretation from another textbook from Salzman 2009. I think he does a nice job of explaining it. And then you'll have to graph the data, and we'll go over how to do that in the lab on Thursday, how to make a graphs. I gave you space for 4 graphs, but you can just do 2 of them. And I included in your homework assignment a link for a video on how to make graphs, how to make pie graphs, and another link to a great website that shows you how to make all kinds of pie charts if you want to make a pie chart, because even though pie charts are not really recommended way of graphing data when you're graphing proportions with small number of categories, it works pretty well. And again, I gave you space for 4, but you only have to do 2. So there's your homework. But let me walk you through the worksheet that gives you an example. All right. If you want to download this and follow along with me, I put it in resources, and I also put it in your homework assignment. This is the chi-square 2x2 test calculation examples, and it gives you an example of how to do all the calculations for the chi-square 2x2 test, with the example of looking at the effects of St. John's wort versus Prozac on being depressed versus not depressed. And it sort of names all of these different cells, right? Step by step. So it says, okay, it's the same. Imagine you had 2 groups of patients, and you had a bunch of patients, and they were all depressed, and then you gave half of them St. John's wort and half of them Prozac, or I don't know, half and half, but some of them St. John's wort, some of them Prozac. And then after 6 months, you measured their depression scores again to see if they were then either depressed or, well, not depressed, to see if there's an association, or, sort of testing the drug efficacy, right? And here we have each cell is labeled. Cell A is the number of individuals that receive St. John's wort and are depressed. And then cell B is the number of individuals that receive St. John's wort and are not depressed. And then so on and so on. Cell C and cell D, those that received Prozac and either are depressed or are not depressed. And then we have row 1 total, row 1 total, column 1 total, column 2 total, and then our total. Again, our null hypothesis is there's no association between the probability of being depressed and the drug that the individuals receive, which means there should be the same proportion of individuals given both drugs that are found to be depressed and not depressed. And if you had really everything divided up in halves, you would have the same number. You have like 25% here and 25% here, but we don't really know how many samples, like how many patients were in each group. So we have to do the calculations to figure that out, what that expected count should be. So again, here it just tells you calculate the observed portion of depressed individuals as the column 1 total divided by the total. That's your observed proportion depressed. That gives you your proportion, right? Column 1 total divided by your total is the observed proportion of depressed. And it's the same thing for not depressed. And then to get the expected proportion, you take the observed proportion of depressed from step 1 above, multiplied by row 1 total, right? Multiplied by row 1 total, whatever's here. So now you see it kind of walks you through step by step. Now we'll go down to where you see the numbers. I think it's a little easier actually to understand with the numbers, but this example shows it to you in like loads of detail. So it'll help walk you through. Okay. Again, column 1 total divided by total. Our column 1 total is 42 divided by our total, like the total number of patients in this study was 83. And at the end of the study, 42 of them were depressed, right? And column 2 total is the total number that were not depressed. And here again, divided by the total number of the study. So then we come up with a proportion. of what that should be, which is 0.59. It's roughly 50-50, right? Roughly 50-50. So the expected proportion of depressed individuals in the St. John's wort group is just the observed proportion of people that are depressed, observed proportion of depressed individuals, 0.560, times the number that were given St. John's wort. So how many were given St. John's wort? 25, right? St. John's wort was 25. So we would expect that the observed proportion of depressed times the number of St. John's wort, row one total, is 0.5060, right? That's our proportion from up here, times 25, which is our total number given St. John's wort from here. And that's our expected number for cell A. Remember, cell A is here, right? Multiply those two together, you get 12.65. 12.65, you pop that up here. You see how this is going to help you do your homework, right? Then to calculate the expected number of not depressed individuals in the St. John's wort group, you take your observed proportion not depressed. Again, that's your observed proportion of not depressed individuals is 0.490, right? Right here. Times 25 again, because that's your total number in the St. John's wort group. And you get 12.35, and that's your expected number for cell B, 12.35. So if there's nothing going on, then you would expect that just as many people who were given St. John's wort would be depressed as not depressed, given the total number of people at the end who were depressed versus not depressed. There'd be no association with St. John's wort or something else, right? And you do the same thing for the Prozac group. You calculate the expected number of, let's see, on number 5, the expected number of depressed individuals in the Prozac group is just your observed proportion of depressed times the number of given Prozac. So we had about 0.5% of the people were depressed, and about 58 were given Prozac. So 0.5060 times 58 is going to be 29.64, right? You pop that in there. Then you just multiply expected number of not depressed individuals in the Prozac group, which is your observed proportion not depressed group, 0.49. It's really interesting that like half the people are depressed. Is that normal? Or is this a sample of people who were depressed to begin with, right? And that's half of them got better, more or less. And then you multiply that by the number who are given Prozac, again, 58. The only thing that's different here, you're multiplying by the proportion of depressed times the number given Prozac, the proportion not depressed times the number given Prozac, and that gives you your expected number not depressed, 28.65 here, here, right? And then if you add them all up, you get the same numbers down here and over here and over here, right? So you'll just do that for our class data and last class data. And then we calculate the chi-square statistic. And it's just this. You take that observed minus expected squared divided by expected. So observed 10 minus expected 12.65 squared. Take that difference and square it, and then divide it by expected, again, 12.65, and that's your first chi-square number, right? And then you can take, again, observed 15, observed St. John's wort not depressed minus expected 12.35 divided by, squared divided by 12.35, and that's your second chi-square number that you get here, and so on and so on. And then once you calculate each one of these, you sum them up, and this final number here is your chi-square statistic. That's your chi-square statistic. And then you could go to a lookup table and you could look it up with our X degrees of freedom, but never mind that. We'll just go ahead and put it into a matrix. Okay. And in this case, you can see you can actually use this. You could copy and paste this into R. And this, you see, it already has the values for you. Your matrix is 10, 15, 32, 26, which matches our observed data, 10, 15, 32, 26, right? Matches our observed data. That's how you make the matrix. And then you say it's a 2 by 2 table, right? And we're going to call that DAT1. Then we say, we look at DAT1, make sure it does actually look like that. Yeah, okay, it looks like that. And then you run the chi-square test. If you did that, if I did this in R, I just did it, you know, I'll just take this. It'll work. This is easy. I'm just going to go over here. And I'm going to say file, new file, R script, nothing fancy, just open up a script. And I'll just paste that in there. And I'll just run this. I created DAT1. I look at DAT1. What does it look like? 10, 15, 32, 26. Just like our matrix. Run the next line. There's our chi-square test. There's our chi-square value, our degrees of freedom, and our p-value. That's it. So is there an association between being depressed and taking either St. John's wort or Prozac? Nope. No association. We fail to reject the null hypothesis. So this is exactly how you're going to do it for your homework. Exactly how you're going to do it for your homework. You're just going to follow along step by step using the example from the example. And you're going to put in our numbers, calculate our expected. Again, the totals will be the same here as there. You're just going to have our expected numbers based on just fill in all the blanks, fill in all, it'll just add it all up. And then put in our observed, expected, square it, divide by expected. And this will give you your chi-square contribution for each cell, which is actually kind of handy because a bigger chi-square contribution usually means there's a bigger sort of difference in that variable or in that cell category. And you'll get your square sum, and then you'll run the test again. You'll put in the number for the female in spring. Pay close attention because I think I put these in the right order to make the table look right. As long as you substitute the number of females for spring and the number of males for spring, the number of females for fall and the number of males for fall. Just look at it and make sure when you look at DAT1 that it looks just like this table here. And then run this analysis, you'll get your p-value, hypotheses, etc. Any questions?
There's a question in the back.
I'm typing in.
The new data you'll get from our class data sheet. Right, okay, so what it should say, I'm sorry, you guys, you're right. Thank you for pointing that out. This should be spring 23, and this, instead of fall, it should be spring 24. Everybody got that? This should be, the top one is spring 23, and this is spring 24. Last year and this year. Fall is us.
Yeah, so wherever you see fall, you're going to put our information in.